Hi everyone, this is the fish. Today we are going to go over multiple signal classification, in short, music. What it gives is like very high resolution peak, and also it's kind of it helps to distinguish objects or targets. Those are closely spaced, and it helps to give the angle of arrival or the angle of the return from the targets. Okay. So again, multiple signal classification, in short, music. And today we're going to go over the Python implementation of this music algorithm. Just going to go over the Wikipedia page. Okay, and here you can see like the peaks. Those are very sharp. And basically we are going to implement this equation. Although like everything looks mathematically very challenging, but I will try to explain in Python, just look into the values and try to explain what's going on there. Okay. And hopefully after that it's not going to look that difficult. So what is the use case? Okay, why do we need to have these higher resolution signals? Okay, so remember earlier we implemented beamforming in Python, and you see like this is kind of quite wide of a peak. Okay, so basically the problem with the beamforming here, the conventional beamforming is like there could be two targets. Like for example, this was done for 15-degree object, but there could be other object close by, and in those cases this will be masked, right? Because this is kind of broad enough. Okay, so it will be hard to distinguish two different peaks. Okay, so the and the beamforming we are talking about, just going to go over some recap. We're trying to measure the angle of this target vehicle, this white vehicle right here. And for example, we have a radar right in the center of this black vehicle, and that is trying to estimate the angle coming from this white vehicle. Okay, so in autonomous vehicles we have radars, camera, and lidars, different sensors. I'm just taking radar as an example, and how it is calculating the target angle using beamforming. Okay, and I just demonstrate like why it could be challenging when we have multiple targets. Usually like in scenario in the road we can have multiple vehicles, and if those are like closely like spaced, or maybe like in adjacent lanes and the center lane, then it will be hard for this beamforming to separate the angle, and that's why we need this super resolution peaks. Okay, so enough of explaining, let's get into the Python implementation. Okay, so we have the use case of like the radar we talked about. For example, we have one transmit antenna and four receive antennas. Okay, and we are going to simulate only for one target in this very beginner level music algorithm implementation. But on later on next chapter, we are going to go over multiple targets, okay, which are closely spaced. But this one we're just going to, for simplicity, just going to have a single target. Okay, so there are several segments here, several steps. First, we need to generate some transmit and receive signal. Okay, so after that, basically we are going to generate a covariance matrix from the received signal, and from the covariance matrix we need to have eigenvalues and eigenvectors. If you do not know what these are, I'll just going to explain mathematically, looking into the values, how they look and how they could be related, and why do we need all these things. Okay, and also from these eigenvalues and eigenvectors we have to separate noise and signal. Okay, and from there we'll implement the equation, the final form of this equation right here. Okay, so let's get started. I'm just closing this page. Okay, and let's generate our transmit and receive signal. Okay, why do we need the transmit and receive signal? Again, you are transmitting a signal, hitting this vehicle right here and getting a reflection back, right? And after that, once we get the receive signal or the reflection, we are going to apply the music algorithm right from here. Okay, these are the steps from the music algorithm. And the first two, that generating the transmit and receive, this is just like simulation purpose. We are going to define what we are transmitting, what we are receiving, and then we do the signal processing right from here. Okay, so let's get started. First, let's generate the transmit signal. Okay, so I'm writing tx here, and for any sinusoidal wave, let's say like we are transmitting a sinusoidal wave. Okay, not going to get into complicated different modulated wave or something else, just having a sinusoidal wave. Okay, so we all know the equation for a sinusoidal wave, right? So tx is, we have the amplitude, then we have this complex exponent. Okay, so this is 2j, f, and t. Okay, this equation we are kind of very much familiar with. Now let's define the variable. Okay, so a is the amplitude. We are having a normalized amplitude, let's say 1, and then we have this exponent. So we already imported numpy right here. Okay, so from numpy library we're going to have this np.exp. Okay, and then we haven't defined the frequency, so let's say our frequency is 1 meg, and then we have the sampling frequency right here, which is 10 times of this frequency f. Okay, and then we have to define the time vector. So to define the time vector, we also need to know or define how many samples we have in the signal. So let's say we have 5,000 samples. Okay, and then from there we can say T is equals to np dot a range. Then we have the samples, and that's divided by our sampling frequency, fs. Okay, and what else? I think we have defined more or less everything. So let's run it and let's plot out the signal. So eld dot plot. Okay, and then let's say we're going to have, so we have 5,000 samples, right? But we're just going to display first 100 samples. Okay, so our time vector t, and then we have the signal tx. Let's take also the first 100 samples. Okay, and since this is a complex number right here, you can see you got to have np dot real. So just taking the real part. Okay, and then run it. Okay, so here we can see our sinusoidal wave. Okay, so now let's move on. Let's define our receive signal. Now we have to pay attention here, okay? Because remember we have 4 receive antennas, right? So I'm just going to go over again on this. So we have transmit TX, and then we have receive antenna, 4 receive antenna, okay? So RX1, RX2, RX3, RX4, okay? And then we have a, let's say, target right here. So one thing I want to illustrate here, we are transmitting a wave, going to go and hit the target, then we are going to receive some back scatters, right? But the signal, we are not going to, all the receive antennas not going to receive at the same time, okay? Because they are physically separated by some distance d, and this distance is in wavelength, okay? So let's define that as well. So let's say our d is equals to 0.5, okay? So you can see, like, just looking into the picture, you can see, like, after hitting the target, they are going to, the receive signal is going to appear at different receive antennas with some time delays, okay? So that's why we have to have a steering vector, okay? That is going to have the responses of this time delays or the temporal. It's just kind of like, think about a filter, okay? Whatever we are receiving, there will be a filter applied to it, and which is just the delay that is caused by the physical separation of the object of the receive antennas, okay? And that's why we are not going to receive everything at the same time. So we have to capture these responses in a steering vector. That's called a steering vector. I think I have explained it in previous beamforming implementation, okay? So I'm just going to comment these things, okay? Now let's define the steering vector, which is going to have the responses of this all 4 receive antennas, okay? So just going to copy this signal from here, okay? And I'm just going to paste it one time. Okay, we have to have 4, so there are 4 responses, right? 1, 2, 3, 4, and usually, like, we start from 0. So RX0, RX1, this is the convention, RX2 and 3, okay? So the amplitude, let's say there is no loss in the environment, which is unlikely, but just for simplicity, I'm saying, like, okay, whatever we're transmitting, we're just getting that back, okay? And then, since it's like the signal is coming in the backward direction, we have to have a minus in front of it, okay? And then this f and t is going to go away, and we'll have d, and which element we're looking at. Let's say we're looking at the first element, okay? So 0. Okay, I think this is kind of self-explanatory. I think I'm missing a pi here, so np dot pi, and then there comes the t end, the first element, which is the 0th element, okay? So we have the response. This is the final form, there are a lot of derivation how you are coming to this part, but I'm just like, writing it like, with some minimal explanation, okay? So this is the response for the first element. So I have it right here, okay? So I'm going to copy it 3 more times. So 1, 2, 3, and 4, okay? So this is the first element. Now for the second element, we're going to have 1 here. This is the third element. So 0, 1, 2, and this is the 4th element, okay? So which is 3. And I don't think we need this guy right here, the 5th element. So just removing that one. That was some extra test. Okay, so we have our steering vector right here. Now, one thing, so we have to remember here, like, we're just simulating a receive signal, right? So let's say this target is at 15 degrees, okay? So I'm assuming, just taking some angle, and the music algorithm doesn't know at what angle the object is located. We're going to find that out, okay? So the algorithm doesn't know where we're looking at or where the object is located in the field of view of the radar. But this signal, we're just, for simulation purpose, we're having an angle here. So angle, let's say 15 degrees. So since it is in exponent, we have to convert it into radians. So angle, right? then we have the angle, and we have to multiply it by np dot pi and divided by 180. Okay, that's how you convert from degrees to radians. And right here you are going to have another term, which is np dot sine of this angle in radians. Okay, likewise here as well, np dot sine, and then okay, here as well, np dot sine. Oops. And lastly, right here. Okay, so I think we have our steering vector. Let's run it and let's look into the values. Okay, so np dot real, and then we are looking to the steering vector. So you see how they are, how the filter coefficient, I should say, looks like when the object is at 15 degrees, or in other words, how the antennas are interrelated. Okay, when the angle, when a return is coming from 15 degrees, if we have some different angle right here, the values will be going to be different. Okay, and the first element is always going to be 1, because that's the 0th element, right? So if you have 0 here, it's always going to be 1. Okay, so nevertheless, like, we have the steering vector, and I think I was able to explain what it is, and then from there we are going to derive our receive signals. Okay, so the receive signal is nothing but Rx is equals to, we have our steering vector, and then we have to take transpose of it, and that's going to be multiplied by our transmit signal. Okay, so this is matrix multiplication. So basically the steering vector is going to be multiplied with the transmit signal. Okay, now why we're taking the transpose, I think this is also explained in the previous lecture, but this is kind of like just for mathematical need, we need to have this transpose, because the number of columns in this matrix has to be equal to the number of rows in this one, and that is why we need this transpose. Okay, so we have our receive signal. Okay, but two more steps we need to do. One is, this is a list. Okay, if you look into the type, you will see it's a list, so we have to convert it into array. Okay, numpy array. So np dot array, then we have s here, and also this is also for mathematical need. Okay, we have to convert it, this transmit signal, also into numpy array. Yes. Okay, so we have everything. Let's run it. I don't see any error here, and then let's plot it out. Okay, so for plotting purpose, we have to do plt.plot. Let's copy this part right here. Okay, that's going to be easy. So pasting it right here, and then this case we will have this Rx signal. Okay, and also one thing is missing, like since we have 4 elements, so let's say this is the first element. Okay, so this is our first element right here. I think I made a mistake here, right? Like this. Okay, so this is our first element, and then I'm copying it 3 more times to have the other elements show up as well. Okay, when we're plotting. So this is the first element, then the second, third, and fourth. Okay, then run everything. Okay, looks like there is some error. Oh, I have to have 3 here. So let's run it again, hopefully. Okay, so what I wanted to show here, the phase difference I was talking about. You see, we are transmitting something, this signal right here, and we are getting the same at the first element, same signal back at the first element, but there are some phase differences, you see, in the second, third, and fourth element. Okay, so that's what we have captured through this steering vector. Okay, so for example, like, let's say the target is at, let's say, 25 degrees. Okay, so run it, and you see the phase difference, they got changed because the steering vector is different now. Okay, so I'm just having 15 here because I'm at the end, I'm going to compare with this guy. Okay, and run it again. Okay, so I think this is clear why we do have phase difference in the received signal and how we are capturing that. Okay, now this thing, oh, okay, so we are just showing the steering vector. So we have a transmit and we have some receive. Now we have to implement the music algorithm. Okay, so the music doesn't know, the object is at 15 degrees. So let's go step by step. So first step is going to create a covariance matrix. Okay, and we are just going to explain what it is. To calculate the covariance matrix in NumPy, it's really easy. So Rxx is equals to, and we are having Rxx because the number of rows and columns is going to be same in a covariance matrix. Okay, so np dot cov, what is that, np.cov, and then the input is going to be the received signal. Okay, so this is just a very simple thing. Okay, we'll now run it. Okay, and now let's look into the covariance matrix. We have a lot of equations for this, but just looking into the values, let's see what we can interpret. Okay, so np dot real and rxx. So the first step of the music algorithm is to have the covariance matrix. Okay, so run it, and there are the values. Okay, so one thing you can see, the number of rows and columns going to be same as I mentioned, and also you see these diagonal elements close to 1, and it's kind of all the values are same. Okay, so this covariance matrix is kind of, for example, just take the first column. So this is the first element, then how it is related to the second, third, and fourth element. Okay, that's what it is explaining. So let's take into the second column. So this is one right here. So we are looking at the second element and how that is related to the other antenna elements. Okay, this is the third, this is the fourth. So this is just the relationship among the antenna, receive antenna elements. Okay, so we have the covariance matrix. The second step is to calculate eigenvalues and eigenvectors from this covariance matrix. This is also very simple in NumPy. We have to have, let's say our variable names are e values, then e vectors. Okay, and then np dot linear algebra, then eig. Okay, so if we have this, it's going to give us the eigenvalues and eigenvectors, and input is obviously this covariance matrix. Okay, so rxx. Now let's run it, and let's look into the eigenvalues first. Okay, so np dot real and e values. So these are our eigenvalues. What you can interpret from this? So you can see all the values are like, very low, but this value is kind of high. Okay, so that is representing the signal. We have only one signal here, right? We are having a single target, right? If we had multiple targets, like for example 2 targets, then we had like 2 similar numbers, and the others should be noise. Let me plot it, and that's going to give you better understanding. So plt.plot, we have this, and let's say star, and then close it, and then let's plot it. Okay, so here it is. So from here you can see like more or less everything is at noise level, and this is a signal right here. Okay, so what eigenvalues does is kind of gives you an idea how many signal component we have in the receive antenna elements or receive signal. Okay, so if we had two signal components, 2 targets, we will have one of this popping up right somewhere there. Okay, so one is signal, rest of these are noise. So from eigenvalues we can definitely say like what is signal and what is noise. Okay, so let's say also, since the algorithm doesn't know, right, how many signals we have, so we have to define like a threshold here. So let's say our threshold is 1. So threshold is somewhere here. Anything above that is signal, and below is noise. There are many ways to get an understanding like how many signals we have, but I'm just taking a shortcut here. Okay, and this threshold you can derive empirically. So let's say we have a threshold of 1, and from there let's say how many signals we have. So n signals equals to, let's say, np dot real of e values right here. Okay, and this is greater than 1. Okay, so what this is going to give us, like true or false. Okay, so if the value is greater than 1, it's going to give us a true. If it is less than 1, it's going to give us a false. Okay, so that's why we have to do this np dot count and then non-zero. So basically that's going to give us a count of true and false. Okay, so let's run this and let's see what these in signals provide. So this is number of signals we have, right? Again, we can look into the plot, but how the algorithm knows how many signals there. So that's why we are defining a threshold and calculating the number of signals we have. So if the number of signals is 1, so let's say how many signals we have in the noise level. So for that, what we can do, just copying this thing, okay, and pasting it right here, and number of, let's say, noise. Okay, and then we have the count non-zero, but only thing we can do here is like less than 1. So whatever is less than 1, our threshold right here is going to be noise. Okay, so run it and let's also look into the noise. Okay, so in noise, number of noise, we have 3. So one question arises, like, we have 4 antenna elements. How many targets it can resolve? Okay, so the number of target the system can resolve is 3. Okay, so always less than 1 of the number of antenna elements. Okay, so if we had like 10 receive antennas, it could resolve 9 signals. Okay, or 9 back scatterers. Okay, so anyways, we have the noise and we have the signal, right? So from here, so this part was needed because from here we are going to have this signal subspace and noise subspace. Okay, but let's first do one thing: np.arg sort and then e-values. Oops, e-values. I'm just going to explain why I'm doing it. Okay. Okay, so we have the plot right here, and if we are sorting the arguments, okay, what you can see, the lowest values, like this is the low value, this is the low value, this is the high value, and this is the low value again. Okay, so what we need to do, we need to separate the noise and signal, right? Let's write it down here. After getting the eigenvalues, eigenvalues and eigenvectors, the next step is to separate noise and signals. Okay, so we already know how many signals we have, we already know how many noise we have, so we have to separate the noise and signals from these eigenvectors. We are done with the eigenvalues, right? Eigenvalue gives you the understanding of how many signals we have. Now we have to play with these eigenvectors to have like the signal subspace and noise subspace separated. Okay, so let's work on that. So already we have sorted out right here, right, from the eigenvalues. So you see, like, this is what we need to do is like have the noises all together and the signal separated. This is not sorted here, right? So we have to sort it. So the way we can do it is, let's say we have the eigenvectors, right? So eigenvectors, we have to sort the eigenvectors. Okay, then eigenvectors right here. Okay, and what we need to do right here is this. Okay, so what this will do is it's going to have, let me run it. Okay, so I'm running it and let's look into the eigenvectors. Okay, eigenvectors. Oops, let's take the real values. Okay, np.real. So this is going to explain you why we had to do the sorting. So let's run it. Okay, so you see, like, first, second, third column, all these 3 are noise, and this is the signal. The very last column is the signal. The idea is to separate the noise and the signal components. Okay, so if we do the sorting of the eigenvalues, and sorting means, like, all the noise components will be like at the bottom, okay, or like at the very beginning, because we are sorting. So 1 2 3, this is no. So before sorting, I wanted to also show how this look like. Okay, so if we plot it here or get the value of eigenvectors, so np.real eigenvector. Okay, let's run everything all together. Okay, right here. Okay, so you see, like, we just did a sorting here. Okay, and now so all the noise components 1 2 3, although, like, I think this is, we had to do the sorting so that now we know all these 3 columns are the noise. Okay, and in the music equation we'll play with the noise. Okay, and we'll explain why we are playing with the noise. Okay, so we have it right here. Okay, now the next thing is, like, we have to get the noise subspace. So let's say Qn is the noise, and then we have the eigenvectors right here. Okay, and then we have this, we're gonna have the first 3 columns. Okay, n signals, right? So n signals. Okay, so run it and look into Qn, np.real, and then we have the Qn. Okay, this is the noise only. Okay, why we are having, oh, because we took the signal, we have to take the noise. Okay, okay, so run. Okay, so you see 1 2 3, the first 3 columns we have, which represent the noise, we have separated from the signal. Okay, and now we can implement, so now we have the noise. Okay, and now we can implement the music algorithm. So now let's say, remember we talked about the equation in Wikipedia page, right? And let me write it down, the equation. So theta we're trying to implement this equation. Okay, so theta music is equals to 1 over, we have the steering vector, we're going to take the conjugate, okay, conjugate of it, and then the transpose. And if I go to the Wikipedia page, you will also see, let me see, music algorithm right here. Just going to go with you again on the equation. Okay, so this is the equation, this Hermitian conjugate. That's why we are writing conjugate and then transpose. So basically these are the noise, u is representing the noise, and we have the steering vector right here. Okay, so first we are having the steering vector right here, complex Hermitian. Okay, and then going to be multiplied with qn, then multiplied with qn dot conjugate, and then take the transpose of that, and then we have the steering vector again. Okay, so this is the equation. We already have the qn, or the noise subspace. Okay, so we gotta have the steering vector again. So steering vector, I think we defined right here, so I'm just going to copy it. So remember, the music algorithm doesn't know at what angle the object is coming from, right? So we have to run through all the angles and try to see the best match. Okay, so I'm just copying the steering vector, which was for 15 degrees right here. So let's say our field of view FOV is let's say our field of view is, let's say, 45 degrees. Okay, so np dot space, I'm just going to show you the values. Okay, np dot pi divided by 4, then np, so this is minus 45 degrees to plus 45 degrees, the total field of view of 90 degrees. So np dot pi divided by 4, and then we have, let's say, we are taking 5 samples. Okay, and before getting into these two, I just wanted to show you this field of view values. Okay, so run it. I'm going to explain it what it is. Okay, these values in radians, so I have to multiply this by 180 divided by np dot pi. Okay, okay, so you see this radar has a field of view of 90 degrees, meaning like it starts the scanning at minus 45 degrees, and it has 500 points, and it can go up to 45 degrees. Okay, we can take other points as well, like 300 points, which will have less calculations. It depends on the what we want to achieve, and I will also show, like, what is the impact of this number of points. But for now, so meaning field of view, meaning the radar cannot see beyond these angles. It starts at minus 45 degrees, it ends scanning at plus 45 degrees. Okay, you can have different values here. You can have 90 degrees, minus 90 degrees to plus 90 degrees. You can have different values. I'm just taking plus minus 45 degrees. Okay, so this is our field of view. Okay, so the next step is just going to run a for loop for I in FOV. Okay, because we are going to look into all these angles. Okay, we don't know where the target is located, so we are going to run through all these angles and going to see where the signal is located. Okay, so that's why we are running a for loop here. So for I in FOV, we are having this steering vector right here. Okay, and then we have the theta music right here. Okay, and one thing I think I'm missing is, like, remember, we have to convert it into numpy array. So s is equals to np dot array. Okay, and then we have this s. Okay, and this is our theta music right here. This is the calculation. Now this is a complex number, right? So what I need to do is take the absolute value of this. Okay, so pasting it here. So np dot absolute value of this theta music. Okay, and also let's have the logarithmic scale. So np dot log 10. You can escape this part, but it looks good if I take this and kind of makes more sense. Okay, so np dot log 10 right here, and this is going to be, since this is some power, we have to multiply by 10 right here. Okay, and the very last thing, we were going to have 500 points, right? So we need some empty array to store all these 500 points. Okay, so let's say our answer is this. So this empty array, we're going to keep everything right here. Okay, so answer dot append, then theta music. Okay, so again, we are running through all the angles possible to find where the signal is hidden. Okay, and we are going to get a peak for sure where the signal is located at that angle. Okay, and where this is kind of, you can get more explanation online, but this is orthogonal. So basically whenever we are getting the match, the signal and noise is going to be orthogonal, so that's where we're going to have a peak. Okay, so hopefully everything looks good. I don't know if there is there will be any error, but let's run it and hopefully there is no error. Okay, okay, I don't see any error, all ran good. Now let's plot it. Okay, so plt dot plot, and this is in degrees, so I'm just going to use it, and then answers. Okay, and then have it plot. Okay, so I don't see anything here, so let's see what's going wrong. Oh, okay, you can see what is going wrong because I'm just having this 15 degrees whatever we had here. So because like we have to go through each of these angles, right? So this is going to be replaced by 1, this is going to be 1, this is going to be 1, and this is also going to be, sorry, I. So this is the iteration, right? We're going through all the angles and trying to find the best match. Okay, let's run it. Okay, oh, here it is. You can see how thin of a peak it is. Let's have a grid plot as well. So plt dot grid, and then we have the grid on right here, and let's run it. Okay, so you see right here we have a peak, and this is the same angle at 15 degrees. You see how broad the peak is, and for 15 degrees you see we have going to have a high resolution peak. Okay, but this is, just looking into the equation, you can see like, we have 500 points, we're going through a loop, it's going to be more computationally challenging for sure. So in general we do not run it for, for all objects. Okay, so let's say our target is at 20 degrees. Okay, let's say where is the angle we embedded here, right here. So let's say the object is at 20 degrees. We're getting a return from 20 degrees. Run it, and right here you see we got a very sharp peak. Okay, and one thing I'm missing is we have to normalize it. So taking the max of these answers right here. Okay, and run this guy again. So this is kind of explaining you like, from the peak what is the noise level. This is kind of 40 dB down. Okay, now I just wanted to look into this field of view again, just going to explain a couple more things. So what is the resolution, or what is the I would say like, if there are two targets separated by, let's say, 1 degrees, definitely it's going to pick it up, because you see the separation here, it's like 0.2 degrees, 0.2 degrees, 0.2 degrees, right? So 1 degree is like more than that, so definitely music can handle that. But at the same time, we are taking 500 points, so it's kind of, it's going to take some time or some memory. So let's say 300 points, and remember the noise floor we have right now here. Now run it. Okay, and you can see, we're going to have more separation from the signal to noise if we have lesser points. But the drawback is, you see, if the objects are like, separated by 0.2 degrees, probably this is not going to, separate those objects. Okay, but again, like, there are some drawbacks and also some pros and cons, so you have to figure out like what are the number of points you're going to take for the simulation. But I think for today, that's all I had to share. What is the resolution of the peak, and how we can achieve a very high resolution peak using music algorithm compared to conventional beamforming. Again, there are some challenges, as I mentioned. In the next lecture, probably going to go over multiple targets, like 2 or 3 targets closely separated, and I'll try to demonstrate how those look. Okay, so for the yeah, take care.